Every neural network you encounter, whether it is reading your handwriting, routing a car, or tagging a face, had its weights tuned by a single algorithm. That algorithm is backpropagation, and it works by alternating between exactly two phases: a forward pass that produces a prediction, and a backward pass that propagates error signals in reverse through every layer to compute gradients. Without it, there is no practical way to train a multi-layer network. The key insight is that the chain rule of calculus lets you decompose a very complicated gradient into a product of simpler ones, computed layer by layer. What makes backpropagation efficient is that a single backward pass costs roughly the same as a single forward pass. No redundant computation, just reuse of the activations already calculated. That bounded cost is what makes it viable even at scale. Training begins with a forward pass. Take an image of a handwritten digit as the input. It enters the first layer, where each neuron computes a weighted sum of its inputs and applies an activation function to produce an output. That output becomes the input to the next layer, which does the same. Mathematically, the full computation is a nested function. For a network with L layers, you apply a weight matrix, activate, apply the next weight matrix, activate, and so on until the final output emerges. Each weight matrix is just a table of numbers, the parameters we are trying to learn. The activation functions are what make stacking layers worthwhile. Without them, the composition of linear operations collapses to a single linear operation, no matter how many layers you add. Sigmoid, tanh, and ReLU are the most common choices, and all must be differentiable, or at least subdifferentiable, because their derivatives will be needed in the backward pass. Once the forward pass produces a prediction, training needs to quantify how wrong it is. That is the job of the loss function. For classification tasks, cross-entropy loss is standard. It measures the divergence between the predicted probability distribution and the true label. For regression, squared error loss, 1/2 the squared norm of the difference between the target y and the prediction y hat is the conventional choice. The factor of 1/2 is a notational convenience that cancels a 2 when you differentiate. Either way, the loss collapses the entire network's performance on one example down to a single scalar. The entire goal of training is to push that scalar as low as possible by adjusting every weight in the network. But with potentially millions of weights, moving them blindly is hopeless. You need a principal direction to move each one. That direction is the gradient, and computing it requires the chain rule. The gradient of the loss with respect to any single weight decomposes cleanly using the chain rule of calculus. Consider a weight connecting neuron I to neuron J. The loss depends on the output of neuron J. The output of neuron J depends on its pre-activation sum, the weighted sum of inputs before the activation function fires. And that pre-activation sum depends directly on the weight in question. The chain rule says, multiply those three partial derivatives together. The partial of the pre-activation sum with respect to the weight turns out to be simply the activation value feeding in from neuron I. The other two terms, the partial of the loss with respect to the neuron output, times the partial of the output with respect to the pre-activation sum, together define the error signal, called delta, at neuron J. Delta is the quantity that backpropagation propagates layer by layer across the entire network. The backward pass starts at the output layer and computes delta for each neuron directly from the loss function. Then it works leftward, one layer at a time. To find delta at layer L-1, you take the weight matrix at layer L, transpose it, multiply it by delta at layer L, and then apply an element-wise product with the derivative of the activation function at layer L-1. This recursive formula is the backward pass in its entirety. It propagates the error signal all the way back to the first layer. The efficiency comes from caching. Every intermediate activation computed during the forward pass is stored in memory and reused here, so no computation is repeated. The total cost of one forward pass plus one backward pass scales linearly with the number of weights in the network, making gradient computation practical even in very large models. With gradients computed for every weight, each one gets updated by a step in the direction that reduces the loss. The update rule is the change in weight wij equals negative eta times the activation oi times delta j, where eta is the learning rate, a positive scalar you set before training. You subtract the gradient because you want to move downhill on the loss surface. Too large a learning rate and steps overshoot the minimum, too small and progress stalls. In practice, training does not compute gradients over the full dataset at once. That would require holding all examples in memory simultaneously. Stochastic gradient descent and mini-batch gradient descent estimate the gradient from small random subsets of the training data. The noise this introduces is not purely a nuisance. It can help the optimizer escape shallow local minima that a full batch gradient descent might settle into permanently. The history of backpropagation is often compressed and frequently misattributed. Finnish mathematician Seppo Linnamäe published The Mathematical Core, the reverse mode of automatic differentiation, in 1970. Paul Warboast then applied it specifically to multi-layer neural networks in his 1974 Harvard PhD thesis, a full decade before the algorithm became widely known. The 1986 Nature paper by Rumelhart, Hinton, and Williams, Learning Representations by Backpropagating Errors, provided the first broadly accessible treatment and empirical validation across several tasks. That paper restarted neural network research and established the algorithm's canonical name. Rapid applications followed. Netok in 1987 trained a network to convert English text to phonemes. Elvin in 1989 learned to steer a vehicle from sensor data. Lecun-Vlanet in 1989 recognized handwritten ZIP code digits. Together, these three applications demonstrated backpropagation's practical reach across language, control, and vision. Backpropagation has failure modes every practitioner needs to understand. In deep networks with saturating activations like sigmoid or tanh, gradients can shrink exponentially as they travel backward through many layers. This is the vanishing gradient problem, and it was the main reason deep networks failed to train for decades before the 2000s. The opposite, exploding gradients, occurs when large weight values cause error signals to balloon layer by layer. ReLU activations help with vanishing gradients but introduce their own issue. A dead ReLU unit that consistently receives negative pre-activation input outputs 0 permanently, and its gradient is also 0, so the weights feeding it stop updating entirely. Beyond these, backpropagation provides no guarantee of finding the global minimum. It converges to a local minimum or saddle point and can stall on flat plateaus where gradients are near 0. Knowing these failure modes is the first step toward addressing them.